We introduce a discrete approximation of the pressure field contact model suitable for use with velocity level time steppers. We demonstrate that this approximation still captures the rich contact interactions provided by pressure field contact, including area-dependent phenomena, while maintaining real-time performance rates. The hydroelastic contact model introduces a virtual pressure field on a compliant body, mimicking the hydrostatic pressure field of a fluid. Dissipation is modeled using the Hunt and Crossley model, and friction is included using a regularized model of Coulomb friction. We follow the trajectory of the contact surface between a compliant ball and a compliant box. The left video shows the evolving contact isosurface as the ball penetrates into the box. The figure on the right shows the one-dimensional pressure and pressure gradient in the normal direction of a single face of the contact surface. Our approximation relates the time rate of this pressure field to the pressure gradients and relative velocity of the two bodies. We simulate a highly compliant bubble gripper anchored to the world, holding a spatula by the handle horizontally. We then command the gripper to alternate between a tight grip, where the spatula is in stiction, and a loose grip, where the spatula is in a controlled slip. This level of grasp control is achieved by properly resolving contact patch area changes. This degree of control would be very difficult to emulate using point contact approaches. The continuous version of pressure field contact requires a rather fine triangular tessellation of the contact surfaces in order to guarantee continuity of the contact forces. This is illustrated with the simulation of the highly compliant gripper on the left. Our discrete approximation does not require such continuity. We exploit this to introduce a polygonal tessellation of the contact surfaces that leads to a significant reduction in the number of contact constraints and a substantial simulation speedup. Our polygonal tessellation is shown on the right. We can see a significant reduction in the number of faces. To demonstrate the effectiveness of our method, we compare results using both triangular and polygonal tessellations of the contact surfaces in a simulation of a relevant robotic manipulation task. Here, the Canova-Jaco arm is tasked with picking up a spatula, scooping and flipping a pancake, and placing the spatula in its holder. On average, the number of faces is 4 times smaller when using the polygonal tessellation. Still, the model is able to resolve the net torque of the spatula needed to achieve a secure grasp while running at interactive rates. A mesh refinement study shows that our solver scales nearly linear with the number of constraints. See the paper for details. In addition, we found the success of the task to be insensitive to mesh resolution. Our collaborators designed controllers in simulation that transferred seamlessly to the real robot. We thank you for watching and encourage you to read the full paper for more details.